Swayam Prabha. Digital India. Educated India.
Welcome to the next class. So last time we basically were looking at the canonical partition function. We also discussed little bit about grand canonical partition function, but our essential focus was on canonical partition function, where we saw that earlier how we derived the ideal gas equation using the partition function obtained in canonical partition canonical ensemble. Similarly, we also saw that the average energy indeed was 3/2 times n times kBT as expected from kinetic theory or thermodynamics, but we encountered a problem, especially when we were dealing with the calculation of the entropy of the ideal gas. Okay. So, just to quickly recap, so essentially, so we were writing our the partition function in canonical ensemble as sum over so e raised to minus beta e where the sum was over energy states of all the gas molecules. So, energy states of all molecules, and we approximated this with e raised to minus beta epsilon, where epsilon is now the average kinetic energy of single molecule, and now the sum is over states of a single molecule, and this whole thing raised to the power n. Okay. So, this was the approximation that we made, all right, that the total energy is basically sum of kinetic energy of all the gas molecules, all right, and therefore, in terms of counting the number of microstates, we can just raise this to the power n, all right. So, that was the approximation we made, and the expression that we got, which we wrote many times in the last class, was 2 pi m kBT raised to the power 3/2, and this entire thing raised to the power n, right. And in the last class, so basically then we proceeded by writing the Helmholtz free energy as negative of kBT of log z, and this we saw that this can be written as n kBT times V by h cube times 2 pi m kBT raised to the power 3/2, all right. There is a log here. Okay. So, this is what we had, and from here we calculated the entropy, which is negative of a partial derivative of Helmholtz free energy with respect to temperature, while keeping V and n constant, and when we did that, we saw that the entropy came out to be 3/2 n kB plus n kB log of V by h cube times 2 pi m kBT raised to the power 3/2, all right. So, there were many things that were wrong here, right. So, we saw that the Helmholtz free energy was not really an extensive quantity, because if I take n to 2n, so f does not scale as 2 times f, because there is a v sitting in here which also scales with 2. And the second problem that we had was that entropy at t equal to 0 is not defined, because it sits inside a logarithm, and later on we also saw that if we undergo this exercises of mixing two ideal gases in equilibrium, we should get the entropy change of that process to be 0, but we were not really getting 0, we were getting a finite number, right. So, and towards the end I mentioned this happened because of the approximation that we have made here, we have made some mistake here, right. So, in some sense what we ended up doing was we ended up over counting the number of states, all right. So, like I said, if we had replaced this v with v divided by n somehow in this expression, which means we basically over counted the number of the number of states, right, and therefore the partition function. And we will see what do I really mean by that term, right. So, what do I mean by the term counting or over counting and so on. So, this is exactly what we will do in today's class, all right. And today we will basically go into the realms of quantum nature of particles, right. And like I use these terms distinguishability and indistinguishability. So, what do I really mean by that, right. And again once we do that exercise over this class or next class, after that we will come back to this and we will try to fix the partition function that we calculated for an ideal gas, and we will see that once we incorporate those ideas of quantum mechanics as well as the concept of distinguishability, we indeed can get the right result, all right. So, that is what we will come back to after some time. So, but before that I will like kind of change topics and not really change topics, but now motivated from this, right. So, we will now consider the reality of molecules or particles that we deal with in statistical mechanics, right. So, so far whatever we had been doing was really classical, right. So, but it turns out the quantum nature of these particles also plays an important role, and let's get into that, right. So, basically what we will do is we will learn about classical and quantum statistics. So, let me go to next page. So, classical and quantum statistics, okay. And essentially what we will look at is since I said that basically we are counting the number of states, right, and the way we do counting really depends upon whether your system is in a classical regime or in a quantum regime, and I will just explain you what do I mean by that, all right. So, in simple words, the system is classical, is classical if number of energy levels is much greater than number of molecules or particles, okay. Molecules, or let me in more general just define it as particles, all right, because there can be some quantum particles as well, particles, okay. However, if system is quantum in nature, if the number of energy levels is much slower than number of particles, all right. So, in the opposite regime we call it a quantum system, all right. And it all boils down to how we actually do the counting in these systems, right. And you can also very easily see that if your energy levels is much greater than number of particles, in classical theory and in classical limit we can assume that our energy levels are continuous, right. However, in quantum mechanics, in quantum statistics, since the number of particles is much greater than number of energy levels, we can also say that if our energy levels are discrete, right, quantized, then we are in a quantum statistics range, all right. So, let me try to explain the difference between these two, all right. So, say okay, so let me juxtapose these two. So, let us say we have classical on this side and we have quantum on the other side, right. And say at any given point we have some energy levels, right. Okay. So, this axis is like the particle index axis, particle index axis, and the y axis is my energy axis. Okay. Y axis is my energy axis. Now, remember what I said. So, in a classical limit, the number of energy levels is much greater than number of particles, right, which means at any given moment my particle will be sitting either here, or it can be sitting here, and it can be sitting here, and so on, right, which means it is highly unlikely for me to find a situation where two particles are sitting on the same energy level, all right. So, that is how we expect to happen in a classical regime, right. Since the number of energy levels is so high and number of particles are so low, it is highly unlikely for two particles to have the same energy. On the other hand, if we now go into the quantum regime, so I will just draw similar schematic again. Okay. So, I am just taking example of 4 energy levels and 4 particles, but in theory there are like trillions upon trillions, right. So, there are like many number of particles and many energy levels, but in quantum limit, number of particles is much greater than number of energy levels, right. So, therefore, it is very likely for me to find a state where there are many particles in the same energy level, right. Okay. So, this is typically a quantum scenario, right, where there is a high probability that, okay. So, again the x axis is particle index, and the y axis is energy. Okay. So, you can see the number of particles is huge. So, therefore, there is a high possibility to find multiple number of particles occupying the same energy state, all right. And in this case, the way we will essentially do counting is will be that particle 1 is in energy state this, particle 2 is in energy state this, and so on. However, the way we count our states changes in quantum state. We say so many numbers of particles are in this energy state, so many number of particles are in the other energy state, and so on, right. So, you should understand this fundamental difference. So, if the number of particles is very low, we can distinguish between these two particles based upon the energy level they are occupying. But in quantum state, since there are many number of particles occupying the same energy, our counting technique changes, right. So, we say so many number of particles are in this energy state, and so on. Okay. So, I will basically slowly go into this how we actually do counting and how it changes the statistics of problem that we are dealing with, but this is like really the at the crux of it, right. So, if you understand this concept, then things will become much easier. Okay. So, maybe I can write down few things. So, in classical, okay, let me put a line here. So, in classical, the counting of states is done on along particle axis, right. So, like I said, I am saying this particle is at this energy, this particle is at this energy, and so on. However, in quantum case, the counting is done along the energy axis. So, in the sense this energy has this many particles, this energy level has this many particles, and so on, right. So, here the counting is done along the energy axis. Okay. So, that is one very important concept. The other concept which is basically also okay. So, before that I can say a few more things, right. So, like I said, since the number of energy levels for classical is much greater than number of particles. So, we expect a system at low densities to behave as classical, right. And and the opposite is true, right, and at high densities to behave as quantum. Okay. So, basically I am making the same statement in a different way, all right. So now let us move on to another concept which is actually related to what I said just now. So, this concept is distinguishability and indistinguishability. So, concept of distinguishability. And indistinguishability. Okay, so let us see how we can conceptualize this concept, right. So, essentially we call two particles to be distinguishable if at all the times we can by confidence trace out the trajectory that it is taking in the phase space, right. So, remember we defined the phase space as the space of position and the momentum, right, and at any given moment or if you track a particle of, or a molecule over certain time, it will trace out certain trajectory in the phase space. But remember there are 10 raised to the power 23 particles in the phase space, right, and they are all, maybe I can assign different colors to it. So, they are all having their own individual trajectories in the phase space, which is essentially chaotic in nature, right. So, the point that I am trying to make is, if you by confidence can say that the particle which I have drawn in red starts from here and it traces out this trajectories over certain time interval, yellow one traces out this trajectory, and if you never lose track of these trajectories, in that case we can call those particles or molecules to be distinguishable, right. So, essentially if we can track the trajectories of particles in phase space over an interval of time with confidence, right, with confidence, then obviously you know which particle is which, right. So, in this case we call them to be, so this situation is distinguishable, right. So, I can distinguish between different particles with confidence, and this naturally means that if you have an ideal gas which is not interacting with where the molecules are not interacting with each other, they are not even colliding with each other, you have distinguishable particles, right. So, which implies a non-interacting. So, that is one example of such distinguishable particles. So, a non-interacting ideal gas is an has distinguishable molecules, right. So, we can distinguish between all the molecules in an ideal gas which is not undergoing any interaction, where molecules are not undergoing any kind of interactions. Okay. Now, what if they start interacting, right. So, now let us try to visualize this process. Say we have two particles, right. So, particle 1 and you have a particle 2, and say they are on course of collision with each other, right, and after some time they will collide. So, this is where they undergo collision. So, you have particle 1 and particle 2. So, this was the trajectory, right. So, this is how they approached each other, and once the collision has happened, so the particle 1 can move here. Okay. So, essentially this is where collision happened, and say particle 1 moved here, and this is how particle 2 approached the collision site and it say diverged here. Okay. Okay. So, if you have a means of determining after the collision what is the actual course taken by these individual molecules or particles after the collision, then we know that then we can distinguish these two particles even after the collision, right. Okay. So, this is basically a situation where they are distinguishable. okay, because I know that after the collision which happened here, the particle 1 got scattered in this direction and particle 2 got scattered in this direction. Okay. And this is but however, say now these particles are not really point particles. Okay. We know that every microscopic particle is basically a quantum particle, right, and we can't really calculate or measure its position and momentum at the same time, right. So, rather than this being a point, so and this is also classical. So, this is also how we treat things classically, right, like billiard balls or something. But if they are indistinguishable, right, and which is like typical quantum scenario. So, rather than the particle 1 being a ball or a point, it is a wave function, right. So, it is a fuzzy ball, right, it is a fuzzy point. So, we do not know where exactly it is, okay, and say this is on collision course with second particle which has its own wave function, right. Say they collide here somewhere, right, and during collision their wave functions overlap so much that we do not really know where is particle 1 and where is particle 2, right. And after the collision has happened, okay, so this is their trajectories, right. So, after the collision has happened, so we know that one particle got scattered in this direction and other particle got scattered in this direction. So, this is okay. So basically what I am saying is, so there is this area where the wave functions are overlapping and we do not really know which particle is which. It is like a black box for us, right, we do not know what is going on here, right. And after this collision which happened in this area, right, there can be two possibilities, right. So, the possibility 1 is that your particle number 1 right scattered here and ended here, right, and particle number 2 got scattered here and ended here. But the other scenario is, which is equally likely, because we do not know what really happened here, because the wave functions were overlapping with each other. This even can be, okay, so this even can be 2 and this even can be 1. So, is that clear? So, maybe I can draw it again on the next page. So, there are two possibilities associated with this, right. So, there was this particle 1. So, this is where the collision happened. So, you can either have particle 1. So, this is where we do not know what is happening because wave functions overlapped significantly. So, either you can have particle 1 here and particle 2, okay, which has its wave function, or the other possibility is, okay. So, other possibility is the particle 1 got scattered here, this is 1, and particle 2 got scattered here, okay. So, both possibilities are equally likely. Right. Since the particles in our case now, they are not really points, they are fuzzy particles, right. So, there is a wave function associated with these particles, right, and in fact we can even quantify this, right. So, if the size of this wave function, right, okay. So, every particle, every molecule has certain dimensions associated with it, right, and also it is a quantum particle, right. So, we can very easily see that okay. So, essentially what is going on is, so here, okay. So, as I said, so wave functions are overlapping, right. So, wave functions are overlapping, and at any given point the width of this wave function can be quantified using de Broglie wavelength, right. So, essentially what we can say that during collision, if the size of the particle, let us say this is A, is greater than its typical de Broglie wavelength, which is h divided by mv, where h is the Planck constant, right, then we know that where is particle 1 and where is particle 2, right. So, this is such a scenario, right. In this case they become distinguishable, right, because during the course during the moment of collision we can very clearly see where is particle 1 and where is particle 2. So, we can like trace out its trajectory with confidence, but if A is smaller than h by mv, right, in which case you have a like single wave function of overlapping particles 2, they become, and we do not know where is particle 1, where is particle 2, because there is probability of finding this particle anywhere over this width, right, they are indistinguishable. Okay. So, I hope this concept was clear, all right. And like I said before as well, so we typically associate distinguishable. So, okay. So, these distinguishable particles, they show what is known as classical statistics. However, indistinguishable particles they show quantum statistics. Okay. So, let us now go into details of this, right. So, let us start with what is known as Maxwell Boltzmann statistics, which is a typically which is a classical and distinguishable, which is valid for classical distinguishable particles, all right. So, let us do Maxwell Boltzmann statistics, which is classical distinguishable. Okay. So, let us see how we can do this, right. So, let us assume we have a system of n distinguishable particles, all right. So, okay, let me draw this box again. Okay. Okay. So, let us say we have a system of okay. So, say we have n distinguishable particles okay, in a volume V volume and total energy E, right. So, total energy which is constant and the volume is also constant and the number of particles is also constant. Okay. All right, and at any given point, like the total energy is E, but we can divide our energy into subgroups, right. Okay. So, let us divide. So, divide energy E into subgroups, right. So, basically if I go to energy axis, right. So, this is energy axis, this is the total energy E. I am just dividing my energy into various discrete units, right. So, let us say the first group has energy epsilon 1, second group has energy epsilon 2, third group has energy epsilon 3 and so on, and let us say we divide them into G number of groups, right, G subgroups. Okay. And correspondingly in every subgroup, say we have n one number of particles in a subgroup with energy epsilon 1 and 2 number of particles in subgroup energy epsilon 2 and 3 and so on up to Ng, right. and okay, and basically what I am saying is, say now I am drawing this in energy axis, right. So, let us say there is so these are the particles where the energy is basically so let us talk about some ith cell, right. So, say in energy space this volume corresponds to all the particles which have energy epsilon I, right, and there are Ni number of particles at any given moment which who have energy epsilon I, right. And let us further divide this equal energy level into more number of subgroups, right. So, say there are Gi number of cells per epsilon I. Okay. So, all these cells have the same energy epsilon I, and there are Ni number of particles which are occupying these Gi cells, which all of them have epsilon I energy, right. So, basically what I am saying is we further divide energy level epsilon I into Gi cells, okay. And basically the main aim of this exercise will be to count how many number of ways are there to distribute these Gi number of particles inside this Ni number of particles in Gi number of cells which have the same energy epsilon I, all right. So, clearly we can see that since this system, the entire system is isolated, it does not exchange heat or particles or anything with the surroundings, with the outside. So, we know that sum over I of this Ni, where I goes from 1 to G, capital G is basically N, and this is a constant. Okay. So, that is one condition, and other condition is that sum I 1 to G of Ni times epsilon I, this is basically capital E, which is constant, right. This is the total energy, this is another constant in the problem, all right. And like I said, the problem now is to calculate the number of ways in which we can distribute Ni number of particles in Gi number of cells, all right. So, let us do that, okay. But first what we have to do is we have to first distribute it, okay. So, first we have to distribute Ni number of particles in energy state epsilon I. So, remember there is total number n in which Ni particles have energy epsilon I. So, how many ways are there to distribute these particles in these energy levels, all right. So, let us start. So, number of ways to distribute n particles into n1 particles with energy epsilon 1, right, and that number is basically NC1, and that is n factorial divided by this is NCN1 and n factorial divided by n1 factorial times n minus n1 factorial, okay. So, similarly we can see the number of ways to distribute now the remaining n minus n1 particles into n2 particles of energy epsilon 2, and that is equal to n minus n1 C of n2, and this can be written as n minus n1 factorial divided by n2 factorial times n minus n1 minus n2 factorial, okay. Similarly, the number of ways in which to distribute remaining n minus n1 minus n2 particles into n3 more particles in energy scale epsilon 3, that is n minus n1 minus n2 C of n3, and I will just write in limited space here, maybe I can write on the next page. So, this can be written as n minus n1 minus n2 factorial divided by n3 factorial times n minus n1 minus n2 minus n3 factorial and so on, right. So, we can just keep on going on up to the energy level and epsilon g, right. So, therefore, what will be the total number of ways? So, total number of ways is basically product of all these, right, product of n c n1 times n minus n1 c n2 times n minus n1 and so on, right. So, that will be product of that, and if you see that it becomes n factorial by n1 factorial n minus n1 factorial times n minus n1 factorial divided by n2 factorial times n minus n1 minus n2 factorial times n minus n1 minus n2 factorial divided by n3 factorial times n minus n1 minus n2 minus n3 factorial and so on. And you can see that all these alternate terms they cancel out, right, and so on. And at the end of the day we will be left with n factorial divided by n1 factorial product of n2 factorial, n3 factorial, so on up to ng factorial, and this can be written as n factorial divided by the product I going from 1 to g n I factorial. Okay. And let us call this number w. Okay. So, first we have calculated how many ways are there to distribute ni number of particles in any energy level epsilon I. Okay. Now, let us go into the second exercise which is basically how to distribute now ni number of particles in GI cells, all right. And this is where we have to now use the principle of distinguishability, right. Okay. So, so now in a typical ith group, so let me draw it, ith group, right. So, a typical ith group looks like this, right. It has an energy epsilon I and there is total number of particles ni, right. And like I said, there are multiple cells with same energy inside this. So, there are GI cells, all right. Okay. So, so let us now calculate how many number of ways we can distribute GI cells into ni particles into GI cells, right. So, the number of ways we can put first particle, okay. So, number of ways first particle can be put in GI cells, right. So, first particle has all the GI cells empty for it, right. So, this is GI, okay. Now, let us ask what is the number of ways second particle can be put in again GI cells, right. And remember, we are not really making any approximation, we are not really making any assumption that whether multiple occupancy is allowed or not allowed, right. So, we are in classical regime, we are assuming that multiple particles can occupy the same state, right. So, particle 2 also sees equal number of cells. So, this is GI, right. Similarly, you can see that if I keep on doing this, so I am just going to get GI all the time, right. So, therefore, the total number of ways, so therefore, total total number will be basically product of GI which is now n times, right. So, because we have ni times, because we have ni number of particles, right, and this is basically GI raised to the power ni, and let us call this pi, okay. And like, okay, so where is the distinguishability coming in, right. So, let us see. So, okay, so this is the case for distinguishable particles. So, let us take an example how these particles are actually distinguishable, right, why this result is valid for distinguishable particles, right. So, let us take an example. So, say let us take a simple example where G is 2 and N is 3, right, which means we are trying to accommodate 3 particles in 2 cells, all right, and let us try to draw it. Okay. So, we have like these 2 cells. Okay. So, we have 2 cells. Okay. So, cell 1, cell 2, and there are many ways we can accommodate these particles, right. So, okay. So, for this formula tells us that there are 2 raised to the power 3, which is 8 ways. Let us see what do they look like, right. So, one way is where your particle 1, particle 2, particle 3 is on the left compartment, right. This is 1. In other case, you can have particle 1, 2, 3 on the right compartment, right. And another way is where you have particle 1 here, but 2 and 3 here, and another way where particle 2 is here and 1 and 3 is here. Similarly, your particle 3 is here and 1 and 2 is here. Similarly, I can have a situation where particle 1 and 2 are on the left and 3 is on the right, 1 and 3 is on the left, 2 is on the right, and particle 2 and 3 on the left and 1 on the right. Okay. And there are this is all the ways that are possible to basically distribute these particles into these 2 cells, all right. So, this is particle 2 and particle 3. I hope that is clear. So, this is particle 2, this is particle 3, right. Now, and you can see there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 ways of doing that, right. But while doing this, we are assuming that we know which particle is 2 and which particle is 1, right. If I had no way of distinguishing between these 2 particles, you can very easily see that all these 3 states would look identical to you if there is no way to put a number on these particles, right. Similarly, these 3 ways are identical and these are different, right. So, we will have 1, 2, 3, 4, much lower number of ways in which we could distribute. But since the particles are distinguishable, we are getting lot more number of ways in which we can distribute these particles, right. So, this is where the distinguishability is going on, all right. So, therefore, to get the final result, okay. So, this is where we are just distributing, we are working with the ith cell, right. But now remember we have G number of cells, we are just doing in the ith energy state, we have G number of energy states. Okay. So, then the total number of ways would be product of this Pi, right. So, therefore, total number of ways will be P1 times P2 and so on up to Pg, and in every case we have G1 raised to the power n1, G2 raised to the power n2 and so on up to Gg raised to the power ng, okay, ng, okay. And this is basically, I can just write it as pi I going from 1 to G, Gi raised to the power ni, okay. And let me call this quantity P, all right. So, now we had earlier W number of ways in which we can distribute these particles, and on top of that there are another P number of ways in which we can distribute Ni particles in Gi cells. So, therefore, the total number of states in this case, and let us call it MB, which stands for Maxwell Boltzmann, is P times W, all right. And you can see the P was n factorial divided by pi Ni factorial, right. So, n factorial divided by product I going from 1 to G of Ni factorial multiplied by pi I, which again goes from 1 to G, Gi raised to the power Ni, okay. So, this is the final result, right. So, this is the how many ways are possible to distribute distinguishable particles in classical limit, all right. So, now our next step is to again the thing that we had been doing before, we are going to maximize this quantity, right. So, and also we work with log of this quantity. So, remember these number of particles is 10 raised to power 23. So, it is always convenient to work with logarithms rather than these quantities as it is, right. So, the step 2 is to maximize log of omega mb. Okay. So, that is the next step. So, let us write what is log of omega mb. So, log of omega mb can be written as log of n factorial plus, so this product will change into sum over I, ni will come in front, ni log gi minus, this product will also become log the summation sigma I times log of ni factorial. Okay. So, this is what we get, and I can rewrite it as follows. So, this can be rewritten as log of n factorial plus sigma I times ni log of gi minus log of ni factorial. Okay. Again we will use what is known as Stirling's approximation, right. So, using Stirling's formula or approximation, right. So, we know log of n factorial, if n is very large, is n log n minus n, right, for large n. Okay. So, let us now use this here. Okay. So, we can write this as n log n minus n plus sigma I ni log gi minus n I log ni minus will become plus ni. Okay. And this I can rewrite as follows. So, n log n minus n plus sigma ni log gi minus sigma I ni log ni, and sum over ni is basically n. So, this is a plus, right, and this will cancel out and we are left with n log n minus plus summation over I ni log gi minus ni log ni. All right. So, this is one of the results. Okay. And now what we are going to do is, so we are going to, so remember this is log of omega mb. Okay. And remember this is a dynamic system, right. So, the number of particles in any energy level, they keep on changing, right. So, since this is still in contact with a reservoir, okay, if I go back to this this schematic. So, our system is in touch with some reservoir which has very high, which is huge, and it has certain chemical potential and certain temperature and so on. So, the number of these particles can like switch between one state to the other all the time due to those fluctuations, right. However, the number of cells per energy scale is the property of the material, right. So, say we have a system, and so the way it is built. So, this is a property of the system, right. So, this gi does not really change with any other parameter, right. So, we are going to okay. So, what we are going to do is we are going to differentiate both sides, right, with respect to ni, since it can change at fixed gi. Okay. And let us do that. So, we can write delta of log omega mb can be written as sum over I of log gi minus log ni minus ni by ni, right. So, I am just taking derivative with respect to Ni. Okay. So, this will become log of Gi. So, I have to do two in parts. So, one will be n so minus log Ni and other will be minus Ni by Ni, right. So, times delta of Ni, right. And we know that in equilibrium. So, in equilibrium, so this quantity will attain its maximum value, which implies so delta of log omega mb will be 0, which implies my sigma I of log Gi minus log Ni minus 1 times delta Ni is 0, and let us call this equation number 1. Okay, and this is the equation that we are interested in solving. All right. But we also have two constraint equations in our problem, right. So, there are two constraint equations. So, the first one is the total number of particles is constant, right, which implies if I take its differential. So, del Ni is 0, and this is my constraint equation, which I am calling equation number 2, and the other constraint is the total energy of the system is also fixed, right. So, this is some E, which implies I epsilon I delta Ni is also 0, and this is, let me call this equation number 3, right. And what we are interested in is we are trying to solve equation number 1 given the constraints equation number 2 and equation number 3, right. And we will solve this using the method of Lagrange multipliers, right. So, use method of Lagrange multipliers. Okay. So, same method that we had used before in kinetic theory to basically get the Boltzmann distribution of speeds. Okay. So, basically what we will do is we will take equation number 1, multiply equation number 2 with some unknown Lagrange multiplier, which is alpha, plus equation number 3 with beta, and equate it to 0, okay, where alpha and beta are unknowns. So, we do not know their values yet, right. So, and if we do that, okay, if we do that, so what we get is sum over I of log of Ni by Gi plus 1 plus alpha, sorry, plus alpha plus beta epsilon I. So, there should be plus 1 here. Okay, let me rewrite this. So, okay, so plus alpha plus beta times epsilon I, that is 0. Okay. So, I am just multiplying this by alpha and this by beta and adding it up here, adding into this equation, and I have just rewritten log Gi by Ni as log of Ni by Gi. All right. So, basically I have just taken minus sign outside. All right. So, that is what I have done, and this I can write as sigma I log of Ni by Gi plus 1 plus alpha plus beta epsilon I is 0. All right. So, now I can simplify this little bit, because since alpha is some unknown constant which is non-zero, right, and I am just adding 1 to it. Okay. So, basically I am just defining another constant. So, in fact what I could have done is I could have basically used alpha prime here throughout, okay, alpha prime, and I can now define, so this is alpha prime. So, define a new constant alpha as 1 plus alpha prime, right. So, I can do that because I am just adding another constant into that constant. Okay. So, therefore, I can write this equation as follows. So, sigma I log of Ni by Gi plus alpha plus beta epsilon I. So, there is a delta Ni which I forgot. So, delta Ni is also here somewhere. Okay. So, we should write delta Ni, and there is a delta Ni here also. Okay. Okay. And delta Ni is basically 0. And since delta Ni is an arbitrary number, right, it does not have to be 0 for this equation to be true. So, this term in the parenthesis has to be 0, right. So, this is true only if log of Ni by Gi is equal to negative of alpha plus beta epsilon I, right, and I can write this as follows: Ni equals Gi divided by e raised to the power alpha plus beta epsilon I. Okay. So, this is beta, and this is an important result. It is still not complete because we do not know what alpha and beta are, but now we know how to distribute Ni number of particles in Gi cells, and this distribution is known as Maxwell Boltzmann statistics actually. And like I said, this is for distinguishable and classical particles, all right. So, in the coming classes we will now move into more indistinguishable quantum particles, and also we will evaluate these unknown constants alphas and betas, all right. So, that we will do in the next class. Thank you.